Now that we know what actually a generator is, remember a generator is something that has a different of potential and makes electrons flow, and we consider not the current flowing from negative to positive, but just from positive to negative because of the convention. And we call the current I, measured in ampere. The difference of potential is V, measured in volt, and resistances are just things that oppose the flow of current, and they're measured in ohm. Now there is there are actually more components in a circuit, and we can go on. We also introduced the Ohm's first law, which is V equal R times I, and all the other that you can actually get from this formula. Or if you are actually more familiar with the triangle and you prefer the triangle thing, you can actually draw a triangle and say, okay, V is at the top, so I'm gonna find V is I times R. I'm gonna find I is V divided by R. I'm gonna find R is V divided by I, and so on and so forth. And we also made a very, very simple and easy example with a battery or a power general power supply, 12 volts, and a resistance of 0.5 ohm. And we say, okay, we gotta find the current that is flowing, I, and the current that is flowing is V, the voltage, over R, the resistance, so it's 12 divided by 0.5, so it's 24 amps. And this is a very, very basic, very, very simple example. Couple of things. The very first one is that, well, it doesn't really matter if you know which resistance is. In practice, we're always gonna have these squiggly lines, and you're never gonna find a circle like this because like it's not gonna happen. They're gonna be way more complicated, and we're gonna get to that later. But please note that we're also considering the current in DC, so basically direct current flowing from one end to the other. I'm gonna talk about AC later on, not in this video, but way later. But it's just to make sure that we're all on the same page here. So we'll all be talking about, we'll all just be gonna be talking about direct current. Okay, so let's introduce something else in a circuit. Let's introduce the inductor. So what is an inductor? Well, I'm just gonna draw the circuit with an inductor. An inductor is drawn like this. This is the inductor, and it's just called with the letter L. The inductor is really just you know something you basically have it's really, it barely reminds you of a spring. It's actually in real life you will actually see it like just something like this, and you will have literally just like a sort of spring getting, you know, through, well, not through, but you know, around this, and the current is just gonna flow through this wire. And you may be wondering, why is that? Like, why are we actually gonna have a wire around something in this way? I mean, what's why are we using it? Well, you gotta know that, as we said before, current is just the flow of electrons through a wire. So in this case, they're gonna flow through this green wire here. Now, if we have a current flowing through a wire, we're gonna have not just current, so an electric field, but also a magnetic field induced by that current. So basically, if we have, for instance, a wire like this, okay, we can use our right hand and say, okay, this is the direction of the current, for instance, or this one instead is the same, is fine. But let's suppose that the current is flowing in this direction, okay? This is I, in this direction, okay? Then the magnetic field that is going to be induced by the current is going to be given by our hand, our right hand, like so. So this is the I, my thumb is pointing to the flow of current, and this is the magnetic field that is created. So it's just gonna be, let me just use another color, like, yeah, I like blue is fine. This is the magnetic field that is generated in this case. So why do we use these inductance? Like, why do we use the wire in this way, and then we go back to, I don't know, like this, like straight and so on? Well, because as I said, moving current actually makes a magnetic field, and vice versa. A magnetic field can actually produce current, which is actually why we are actually having, producing current with magnets. But I'm gonna go to that and explain that way later, because that involves three-phase current and so on. But anyway, the flow of the current induces a magnetic field, and a magnetic field can induce a current. So having these inductance here, when we draw this, we just mean this, and we mean that, okay, we're gonna have a magnetic field stored here, which can be useful because, it can actually be useful to, just regenerate current out of the magnetic field and increase current for whatever reason and so on. So this is actually very important. Another thing I'm gonna be talking about is the capacitor. Now the capacitor, I'm just gonna make another very simple circuit. It's something that looks like this. Like the generator I drew before, like this, but with the top one of the same length as the bottom one, like so. Oh, by the way, I didn't say that the unit of the inductor, so of the inductance, is the Henry. Okay, so Henry, we measure it in Henry. We measure the generator in volt, different of potential, resistor in ohm, the current I measure in ampere, the inductor, so it is called L, and the inductance is measured in Henry. And then we have the capacitor, which is C, and is measured in farad. Now, what is a capacitor? Well, a capacitor is actually made of two plates, two metal plates, and when we apply different of potential from here, so the current is flowing here, we're going to have the positive charges accumulating on one plate and the negative ones accumulating on the other plate. In the middle, they're not touching, so we're going to have nothing like we can have air or other gas, other kind of gas. But you know, generally, the part thing is that you're going to have two metal plates, and capacitor can actually be like this, like very simple. Or they can also be I'm really terrible at drawing things, but I'm gonna try to draw it correctly. Let's see if I can just do it. Yeah. We can also have those kind of capacitor, circular ones, in which we have the same two metal plates, but instead of being like, like this, they're actually circular, and one is inside, and the other one is on the kind of outside. And here in the middle, we will actually have either air or a gas, and so on. So this is a capacitor. A capacitor actually acts up like it generally split, and we can actually say that it's like a resistance. Like I'm just gonna draw a box because I don't want to draw a resistance, and eventually a generator. Why do I say this? Well, because a capacitor is actually storing current. Is we're starting our circuit, the capacitor is discharged and is actually current is flowing, we have a difference of potential, and the capacitor is actually storing current. So in this case it's actually acting like a resistance. If we have a switch, and I'm just gonna introduce the notion of switch, okay? There we go. Now we have the capacitor, and we have the generator. Yeah, let's just say that here we have another resistance. Okay, this is a simple circuit. Let's assume that we have our generator here, our switch here, our resistance here, and our capacitor here. So and suppose that we are at t equal 0, so time equals 0. The switch is open, okay, like this. The circuit is not closed, so nothing happens. The capacitor is discharged, doesn't have any anything inside. It didn't store anything. I just discharged, and there is no current flowing. Everything is stationary. Everything is, nothing is moving. But then, if we go to t equal to, I don't know, 1, the switch is actually closed, okay? So the switch is closed, like so. And we have our generator, throwing current through both the resistor and the capacitor. By the way, those two are in parallel. We can have things in parallel, like so, like parallel, and in series if they are like one next to the other, like this, those will be in series, okay, but those two are in parallel because we have you know, those things split. I'm gonna talk a little bit more about series and parallel, but right now just bear with me. So we're at t equal 1, the switch is closed. Okay, so the current is flowing and it's going through the resistor and also through the capacitor. Now what happens? Well, the capacitor is actually acting like a resistance and is storing energy. So if we go now to, let's say, t equal 2, okay, like 0 second, 1 second, and 2 second, but that's fine. T equals 2, we say, okay, now we're gonna open the switch again. So the generator is not gonna be connected. Like there is a switch, the generator is not connected. We only are going to have the resistance and the capacitor. But now the capacitor has stored some energy because there are positive charges and negative charges on one end and to the other. So remember, the negative charges are gonna try to get to the positive one, but for the sake of computation and so on, we just think that the positive are gonna go to the negative. So the current now is gonna flow like so through the resistance, and the charges are gonna go you know, from positive to negative, positive to negative, positive to negative, again, again. And the capacitor is gonna slowly discharge itself by making current flow through the resistor and getting there at the very bottom. So then let's say again we are at t equals 3 seconds. Our capacitor is discharged in the sense that it doesn't have energy anymore. So the current is no longer flowing, and we're gonna close the switch again, and everything is gonna start once again. Please note that the capacitor is very, very, very useful, literally very useful. For instance, I'm pretty sure you are familiar with, you know, even if you are not a photographer, you all take pictures, right? If you are with a camera and you take a picture, you know, during the night, yeah, sure, you can raise your ISO up and so on and get all the noise, but this is not the point, not right now. The point is that you almost definitely want to use the flash, but in order to use the flash, you're gonna have a capacitor. Why is that? Well, because, you know, your camera actually has a generator, which is just a battery in DC direct current, which is making current flowing through the circuit like this way. But in order to have a flash, so photons going out from the flash, you're gonna have a lot of energy, like literally a lot of energy. If we would have to, you know, connect the power supply directly through the flash, we wouldn't have a flash. We would have just like, I don't know, like nothing, like, you know, it wouldn't be a flash. Like if we would have something like a light emitting diode, which I'm gonna talk about later, we would have like a little bit of light, but definitely not a flash. So in order to do that, we're gonna have a capacitor. So the capacitor is gonna store energy from the battery, and then you're gonna be able to take a picture, and the capacitor is gonna release, boom, all the energy to the flash at the very same time, a lot of it. It's gonna be totally discharged. But this way, you're gonna be able to, you know, take a picture. There are many other things in which that the capacitor are used for, but I cannot tell you right now because I haven't introduced the concept of, for instance, AC, so alternating current yet, so I cannot talk, many other things, so I cannot talk about them so far right now. So, but anyway, capacitors are really important, like honestly, really important. So yeah, that's pretty much it. In next part, I'm gonna be talking about the diode and the light emitting diodes, which, by the way, they're just the LED, which I'm pretty sure you know, but not everybody actually knows that LED actually stands for light emitting diodes and what diodes are. So I'm gonna be talking about them a little bit next.